But when VGS is less than VT, then this current is not to be there, but it will exist because of the parallel field or horizontal field. There will be, even if VGS is 0, then also some current will be there, because dimension, drain to source dimension is so less now, only or rather less than 20 nanometer. Earlier it was 20,000 nanometer. Think of, note that I sub can occur even when there is no switching activity, obviously. So in both the cases it will be there. Switching activity is there, then also, otherwise also. I sub exponentially increases with the scaling of the device threshold. Device threshold is decreasing gradually. Earlier it was more, maybe 1 volt, 2 volt, when supply voltage was 5 volt. 0.7 volt, 0.1 volt, 2 volt, even 2.5 volt is not a problem. VT could be that much high because VDD was 5 volt. But as the scaling has been done, technology scaling, device dimension not only has been reduced, vertical as well as horizontal, but supply voltage has been reduced, has to be, okay. Without decreasing the supply, supply voltage, if you reduce the only device dimension, then what problem will occur? Tell me, somebody. Scaling, we have discussed at the beginning of this module. What will happen?
Sir, can you repeat the question?
Suppose, while technology scaling, you are reducing the dimensions, vertical as well as horizontal dimension of the device, but not the supply voltage. What will happen?
So then electric field increases and
electric field will increase.
High field
electric field will be increasing. So what is the vertical dimension, by the way? It is oxide thickness.
Yes,
isn't it? We have discussed all those things. So oxide thickness is 300 nanometer to now less than 1 nanometer. So what will happen if electrical field, vertical electrical field is too high, VGS is too high, and oxide thickness is too less, then it may not be able to withstand that electrical field. It will be punctured, or you can say that gate leakage will be used. Hot current injection we have discussed. SCI. Yes or no? Not discussed.
Yes, sir.
Okay. No more. See, subthreshold leakage current is expressed as I sub dependent on VGS and VDS equals to I naught into VGS plus VT by eta VT into 1 minus e to the power minus VDS by VT. This VT is thermal voltage and this VT is threshold voltage. Okay. I naught equals to mu 0 COX W by L VT square, and VT equals to KT by Q, 26 millivolt at 300K. COX is the oxide gate oxide capacitance. If mu 0 is the zero bias mobility and low field mobility, you can say. Okay. And W by L is the width over length ratio of the device, and eta is the subthreshold swing coefficient. And we have discussed, I think, regarding this subthreshold swing coefficient, isn't it? Yes?
Yes, sir.
Okay, then, quickly. Now, in addition to the 3 major sources of power consumption, P dynamic, P static, and P short circuit, in CMOS digital integrated circuits, some chips may also contain pseudo-NMOS circuits, which will continuously draw current or power from the VDD. We know that if V in equals to 1 and MOSFET is on, and since PMOSFET is always on, there'll be a direct connection from VDD to ground. Okay, so this thing also we have discussed earlier. Pseudo-NMOS we have discussed or not?
Yes, sir.
Total power dissipation can be expressed in this equation. P total equals to alpha T, or alpha simply CL VD square FT. Alpha is what? Activity factor. FT is transition frequency. CL VD square, you know, VDD into I short circuit plus I leakage plus I static, where I short circuit denotes the average short circuit current, or ISC, or we can say IDP, direct path current. I leakage denotes the reverse leakage and subthreshold leakage currents. It is covering all those leakage currents just now discussed. And I static denotes the DC component, DC current component drawn from VDD in case of pseudo NMOS logic. This is here in this particular case, it denoting the current due to in static condition current due to pseudo NMOS. If there are pseudo NMOS circuits gates in your total system. The switching power dissipation, which is the first term in the equation, this is the switching power dissipation. P dynamic is the dominating component in most CMOS logic. But today, if you see, then static power is becoming very high, comparable to dynamic power. Now we are going to discuss the power delay product, energy delay product, etc. Power delay product, it is the multiplication of power dissipation into TP, propagation delay. Okay, it measures the energy needed to switch the gate. PDP is equal to P average into TP. Okay. PDP is the measure of energy. If we assume that this gate is switched at its maximum possible rate of F max equals to 1/2 TP, then ignoring the contributions to the static and short circuit or direct path currents to the power consumption, PDP becomes this. PDP equals to P average into TP, where P average is CLVD square into TP. CLVD square F max into TP, that is CLVD square by 2. This is the expression, half of the energy taken from the battery. The PDP gives average energy consumed per switching event. This for a 0 to 1 or 1 to 0 transition. Remember that earlier we had defined E average as the average energy per switching cycle or per energy consuming event. As each inverter cycle contains a 0 to 1 or 1 to 0 transition, the average hence is the twice of the PDP. Okay, PDP is the half of energy taken from the battery when the gate is switching or making a power consuming transition. We have already seen that energy taken is E energy taken from EVDD is equal to CL VD square, and out of which energy stored ECL, energy stored in CL is up that CL VD square by 2. Other half is wasted in what? Dissipated in P MOSFET. Okay, and this half, this happens when the output node makes 0 to 1 transition, and when 1 to 0 transition occurs of the output, then this half also is grounded by RP, resistance of RN, resistance of N MOSFET. It is dissipated in resistance of N MOSFET. Yes, is it understood?
Yes, sir.
This discussion is this discussion is already known to you. Shashank, yes, Shashank and Kartik Rai.
Sir, I'm present.
Yes, sir.
Both of you, okay.
Yes, sir.
Join timely. So, as can be seen from the equation, the number PDP can be reduced by reducing the supply voltage VDD. Obviously, CL VD square by 2 is the PDP. So if you reduce the supply voltage, then this PDP can be reduced, but at the expense of performance. If you reduce the supply voltage, what will happen? Charging of the CL will take longer time. Understood? So circuit may be slower. A more relevant metric energy delay product combines the measure of performance and energy, both. Okay, takes together. The EDP is defined by PDP into TP or P average into TP square. CLVD square TP by 2. So these all things will be used, this definition of TP, then power, average power, and then PDP, when I'll be simulating some circuits for it. Okay, a SPICE simulation and show in the class only. Okay, during that time, you will remember these definitions. It will be useful. In a digital circuit, they are the main design metrics you should consider. Means once you are comparing your circuit with another circuit, you must compare with respect to these parameters or design metrics. Okay. In case of analog circuit, maybe gain or gain bandwidth product, etc. But here in digital circuits, these are the design metrics. So if NMOS and PMOS transistors have comparable threshold, BTN almost equals to BTP numerically, and saturation voltages, we can simplify the propagation delay expression as TP equals to, we have already written TP equals to TP LH plus TP HL divided by 2, average of these two. Okay, where with this some assumptions, we can write the expression of TP as TP equals to alpha CL VDD by VDD minus VTE, where VT is the VT plus VD set by 2, and alpha is the technology parameter. The equation, this equation and previous equation of this ADP can be combined to get the expression of PDP as alpha CL square VDQ by 2 VDD minus VT. Remember, VT is this value. The optimum value of supply voltage, once you are designing circuits, at what supply voltage, I mean, you will get the optimum value. Say EDP, delay as well as power consumption is optimized in such a way that neither, if you are reducing the say power consumption, for that you are decreasing the VDD, your delay will be too large, long delay. That is also not acceptable. So some optimum VDD can be found, and expression for that is VD OPT equals to 3 by 2 VT. VT already written. Okay, VT equals to VT, threshold voltage plus VD by VD sat by 2. The above analysis implies that the optimum VD has a value which simultaneously optimizes the performance and energy. Okay, means performance means your TP actually, and energy means your PDP. Okay. For the submicron technology with VT equals to 0.5 volt, the optimum supply voltage is around 1 volt. Okay. And this book is written when the technology generation was 0.25 micrometer, supply voltage was 2.5 volt. This comment is based on that technology generation, right? Might have simulated, shown they have got the result and then commented that VDD OPT is around 1 volt. Okay, but we have also done the similar kind of analysis at 22 nano technology generation. Quite deep submicron technology, you can say, or nanometer technology generation. It is okay. The MOSFET is so less in dimensions and supply voltage is so less. So in this, supply voltage is 0.8 volt and T-aux is 0.8 nanometer. So once we did it, what we got is this 827.25 millivolt is the optimum VDD. Okay, not 1 volt as per our analysis. Now, how you get this expression? Expression VD opt equals to this. We have already written this VD OPT, where it is VD OPT was VOPT is 3 by 2 VTE, where VTE is equal to VT plus VT divided by 2. So how it is obtained? It is differentiating some equation. We have got it. If you want, take the snapshots and study. It is found in our one of the paper. Okay, you'll find this detailed derivation in the paper. Otherwise, in the book, it is written how to get this expression. This same thing we have done. The optimum value of supply products can be obtained by taking the derivative of equation 57. Okay, with respect to VAT and equating the result to 0. That is the same thing we have done here to get this expression. Now, our module 1 is over. Now we have to start the module 2. Okay, but let us discuss before that when your quiz will be conducted. Quickly tell the date, propose the date.
This Sunday evening.
Sunday time. I'll note down somewhere.
Evening 6:30.
Evening 6:30. Everybody agreeing with that?
Yes, sir.
Yes.
VLSI systems quiz on Sunday. Sunday means what is the date? 19. Sunday.
19.
Yes, sir. 19, sir.
It is 19. 19/9 at 6:30 p.m. Okay. We have discussed switching threshold, VM, noise margin, formulation, dynamic behavior was computing the capacitances, propagation delay, and propagation delay perspective, the energy delay product, etc. Everything is discussed. Static power consumption, putting it on. Anything left over is this portion. Analyzing power consumption using SPICE. So whatever you saw today, average power, etc. I'll be sometimes later on simulating the circuits. Okay. Simulating the circuits. Should I do now? But before that, let me do one thing. For the second module, I will upload or send some. Do you have the common email address? Common email address of these students. I am interested in these students only who are studying this. I'll send the video quickly.
Sir, we have a WhatsApp group, sir.
WhatsApp group. Can I send to WhatsApp group?
Yes,
This,
sir, definitely. All of
WhatsApp group of this Vlsi systems only.
Yes, sir. Of VLSI system. I added you and all the students as well.
No, I think that is for in-depth specialization only.
No, sir. Apart from that, we have another for all VLSI students as well.
Okay, then give me that. How can I send it? Let me WhatsApp group these subjects. Now, specifically, we'll now discuss interconnects and its issues in module 2. So if you go through, you'll be understanding and I'll be going fast in the class. Within 1 or 2 lectures, I want to finish because I have taken a lot of classes here. So let me add the documents which are here. The whole thing will be adding.